Hai, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Arief bin Muhammad Anuar. My matrix number is 2022610776. Today I will be presenting for the assignment of the subject ETS551 Digital Signal Processing. So let's go. So introduction is video. I will explain the design of a finite impulse response low-pass filter using any window and the design of an analog notch Butterworth filter for power line interference suppression. So for FIR filter design, so this is the question. So the first part is to sketch the magnitude response. Basically, this is the sketch of the magnitude response. As you can see, the stop band start from 1.5 kilohertz until 2.5 kilohertz. For the pass band, it starts from 0 until 1000 before it drops into negative 45 dB at 1.5 kilohertz. So FI filter design using handling window. The handling window is one of the most commonly used windows. It gently tapers the edges of the impulse response to reduce spectral leakage. One of the property of the handling window is its stop attenuation, which is about 44 dB. So FI filter design, design using handling window. Basically, the first step is to use the ideal impulse response, the ideal equation which we obtain from the appendix, and then we do normalize frequencies. For passband edge, we get 0.4 pi. For the transition width, we get 0.2 pi. And next up, we have to determine the cutoff frequency, which we get 0.6 pi. And then we apply the handling window, which is Hn equals to Hd. For the handling window, VWN equals to 0.5 minus 0.5 cos 2 pi n over n capital, which we also obtain from the appendix and table. For the equation, for this filter, we get Hn equals to Hdn multiplied with Wn. Ideal response multiply with handling window. So for the table reference, and then we have to find the causal FIR for N32 to 34. So these are only the theories. So these are the calculations that I made. So for 32 we get 0.00014. For H33 we get 0.0052. For 34 we get negative 0.00109. And for the filter coefficient, altogether we get Hn. Inside of Hn we get 0.00014. In the middle we get 0.0052, and the last one we get negative 0.00109. And next up, we design the Butterworth filter design. So for the question, we get in a power quality, we have to design a analog notch Butterworth filter to suppress 60 Hz or 50 Hz. 50 Hz for the standard in Malaysia. Power line interference from current and voltage measurements. The system must preserve transient events such as voltage as well harmonics. Blah blah blah. So the requirements are passband ripple must be below than 27 dB. Stop attenuation must be greater than 40 dB, and the passband cutoff frequencies are at 0.3 pi, which in radian, and does not need to be converted. And also for the stop band cutoff frequency, we get 0.5 pi, also in radian. So we have to first off we have to determine the selectivity factor K, the discrimination factor D, and filter order. So for the discrimination factor, we use the formula, and we get 0.2237. For the selectivity factor, we use the ratio between passband and stop band cutoff frequency. We get 0.6. And for the filter order, we use the log 10 n greater than log 10 discrimination factor over log 10 with selectivity factor, and we plug in the values and we get 2.093, which then I rounded off and we get 3. And I start to determine the 3 dB cut frequency to any value within the range. So we use this formula. So and then we plug in the parameters that we have identified beforehand. And for the cutoff frequency, the 3 dB cutoff frequency we get estimated at 0.3365, in between 0.3384 and 0.3345. And then we have to determine the system function based on calculated left hand side poles. So this is the equation that we will use, and this is the for the n 0, 1, and 2. So for n0 we get negative 0.16825 minus j 0.2914. For the n1 we get 0.336 negative 0.3365, and for the n2 we get negative 0.1685 plus j 0.2914. And then we plug in into the HAS, which we get 0.0381 over with S plus S0, the S plus S1, S plus S2, the final answer. And then we verify through MATLAB using some coding. The coding is based off the parameters given, and so summarization of the summarization between the MATLAB verification and the calculated we get for the filter type analog Butterworth, transfer to digital manual calculation. For the MATLAB simulation, we got digital Butterworth via Butter and bilinear, the coding that we use. So filter order n3 rounded from 2.93 for calculation, and for the MATLAB simulation we get n3 with digital Butterworth filter. We see above the first graph. And cutoff frequency we get 0.3665. For the MATLAB simulation we calculated via work formula. So for frequency response, expected small low pass response. For the MATLAB simulation we convert with frequency Z plot. And the final result is design is valid for specification, design meets all specs per MATLAB output. So for conclusion, the theoretical design and MATLAB validation align perfectly. The filter successfully meets the requirements with smooth attenuation around 0.5 pi and ripple below 27 dB. And hence, this confirms the Butterworth filter is suitable for suppressing 60 Hz noise while preserving signal integrity. That is all from me. Thank you.